I, Amit Agrawal, Rex Fernando, and Benny Pincus, and Amit will give the talk.
Hi everyone. So today I'll be presenting this talk on thresholdizable batched identity-based encryption. This is joint work with my co-authors Rex Fernando and Benny Pincus. Um, so without going much into the title, let's first start with the motivation. So the motivation is the following. So suppose you have many ciphertexts floating around, which are encrypted under a public key encryption system, for which the respective secret key is sort of threshold shared among some set of servers. And at a future point, we want to select some subset of these ciphertexts and sort of do a threshold decryption for them. So the servers would be provided with the subset of ciphertext that needs to be decrypted. The servers would do some kind of communication between themselves and then release some sort of information which would help you decrypt all the ciphertexts that were part of this subset while preserving the privacy of the ciphertexts that were outside the subset. So the efficiency question is, we want this communication between the servers to be low. What do we mean by low? So let's say capital B is the batch size, meaning the number of ciphertexts that were in this subset. We want that the communication cost between the servers holding these threshold key shares should be much smaller than B and ideally independent of B. And this problem has also been known in the literature now as batch threshold decryption. And one motivating example is this mempool privacy application. So imagine a blockchain setting where clients are sending their transactions. These transactions first get included in some public mempool. And then some subset of these transactions are selected to be part of the block by validators in a blockchain. And the problem is because the mempool is public, this opens up opportunities for these attacks like front running and other such attacks. And so one idea that has been floating around for a while is why not, instead of sending plain text transactions, encrypt these transactions and then send it to the mempool. So now mempool has encrypted transactions instead of plain text versions. And some subset of these ciphertext encrypted transactions would be included in the block. And only after the block is finalized, we would decrypt the transactions. And the idea is that once you build the block, at the time of block building, the content of the transactions are not known. So this will mitigate some attacks of inclusion of transactions which are based on the content of transaction. So at this point where you want to do decryption, you want this decryption process to be efficient. And ideally, you want to decrypt this batch of ciphertext in a communication efficient way. Okay, so there are some existing approaches in the literature which try to solve this problem of batch threshold decryption. So let's say N is the number of servers and B is the batch size, the number of ciphertext that we want to decrypt. So let's say if you just use naive threshold encryption like threshold El-Gamal, then the communication between servers scales linearly with the batch size because you have to communicate for decrypting each ciphertext individually. And also the computation grows linearly with the batch size. Now, there was an interesting work by Chaudhary et al. In last year, which showed that you can push the communication to be independent of the batch size. So no matter how big the batch size is, communication doesn't scale with the batch size. And also it has better computation. But the problem is that this protocol required a setup phase to be executed for every batch. And this setup phase is quite expensive. And so in our work, we show that you can basically get the same computation and communication metrics as the previous work, but without having this per batch setup phase. And also the construction is quite natural, as you will see. There are some other related works which use threshold IBE, but these works do not achieve the privacy guarantee that we want. Basically, we want that the ciphertexts that are not part of the batch should not be decryptable. So whereas if you just use threshold IBE in a naive fashion, everything would be decrypted. And there are many concurrent works which two of them have similar construction as ours, and one other construction which is based on a completely different design, all trying to solve the same problems. These all works came around the same period. Okay, so let's look at the high-level design. So this was our picture from some couple of slides back. So we have a batch of ciphertext, and the key is threshold shared among the servers. And so as a first step, we will start associating each ciphertext with some ID. Think of these IDs as, let's say, just field elements. And these IDs are unique for each ciphertext. And now we select some subset of these ciphertext, and we want to decrypt them efficiently. So as a first step, what we'll do is we'll take the IDs of the ciphertext that we want to decrypt, and we will form a succinct digest out of it. Think of Merkle hash for now, just as an intuition. And then this digest will be passed on to the servers, and they will do some kind of processing on this digest. Now, the digest itself is constant size and small, independent of the batch size. So this processing is also some constant size processing. And once this processing is done, these servers would release some succinct key, succinct as in the size of this key is independent of the batch size, which would enable the decryption of all the ciphertexts that were part of the subset. So this is the high-level design. And we want that this communication that happens between the servers during this processing phase is low. Again, by low, I mean something which is completely independent of the batch size. And we call this schema as thresholdizable batched identity-based encryption. The reason we call it identity-based encryption is because, as you can see, each ciphertext is associated with that ID. And batched in the sense that now the secret key that you issue for this multicolor secret key is for a batch of identities, not a single identity. And thresholdizable, it means that the issuance of that secret key for the batch is thresholdizable among a set of servers. Okay, so now I'll go into the cryptographic toolkits that we use in order to build this key. So first is an accumulator. Think of like Merkle hash as an intuition, and a thresholdizable digital signature scheme. So we'll use these two ingredients and build this object thresholdizable batched identity-based encryption using these two. And so coming back to the high-level design, what we'll do is basically to create this digest, we'll use an accumulator scheme. And the key that would be shared between the servers would be a signing key of some digital signature scheme. And the processing that is done on the digest would be a threshold signing process. And this key would be a digital signature on the digest. So now looking at the schema, what we want is the following. This is the main thing. So we want the decryption of a ciphertext to be possible if two conditions hold. One, that the corresponding ID of that ciphertext is included in the digest D, and there is a valid signature on this digest by the servers. So if these two conditions satisfy, the ciphertext should be decryptable, otherwise it should not be decryptable. And so we want to create an encryption scheme which help with where the decryption happens if these two conditions are satisfied, but it's not clear how to do this directly. So let's start with some preliminaries. So accumulator. So an accumulator allows you to compress a large set into a succinct digest using some commit algorithm, for which later you can create opening proofs for elements which are in the set. And there's a verify algorithm which, given a digest proof, an element outputs either accept or reject. Correctness says that you can proofs produced for items in the set will always accept. Succinctness means that the digest is small, sublinear in the size of the set, and binding means that it should be infeasible to compute opening proofs for items not in the set. We also use digital signature. I'll just skip this slide as most of you are familiar with digital signatures. Okay, so now we have to use these two ingredients in order to create some kind of witness encryption scheme. Witness encryption is something that we'll build towards. This is not something that we'll use for our construction. So in a witness encryption scheme, you have some NP language L specified with some relation. And when you encrypt a message, you encrypt it with some instance in the language. So instance is X, and you create a ciphertext CT. And to decrypt, you have to produce a corresponding witness for the instance. And again, the correctness says that if the instance witness pair is in the NP relation, the decrypt successfully outputs the message. And security says that if the adversary doesn't know the witness, then the message is hidden. So in principle, you can just use general purpose witness encryption scheme to solve the problem that we are trying to solve. But the challenge is that general purpose witness encryption schemes are quite inefficient. So the solution is, can we design a special purpose witness encryption for this specific task that we have at hand, where we have a very specific relation that we want to check. And we name this scheme basically as batched identity-based encryption. And the observation is that if the relation that you want to check has some nice property, then you can create an efficient witness encryption scheme out of it. And what I mean by this nice property is something that has been used in many recent works, is that if the relation that you're verifying has the function that you're computing on the witness is linear, then you can create an efficient witness encryption scheme out of it. And when you're using pairing-based constructions, this means that you should never be pairing a witness element with another witness element. And if this is true, then you can build a witness encryption scheme out of it, which we'll see in the next few slides. And so the entire novelty boils down to how you select your ingredients in such a way that you can conform to this nice property. So the ingredients that we actually use is the KGG commitment scheme for the accumulator and a modified form of BLS signature scheme that we'll see now. Okay, so before going into the construction, just some notations. So we use a pairing-friendly cryptographic group specified by this triple of groups G1, G2, GT. And we'll use the circle notation for denoting the pairing operation. And we'll use the additive notation for groups. So if you have a group G sub I, then for generator G sub I in a group GI will be denoted by this bracket notation, 1 subscript I. Think of the thing inside the bracket as basically the value in the exponent. So yeah, so G to the X would be denoted by this bracket notation X. And so using this notation, if you want to pair G to the X and G to the Y, you will get G to the XY in the target. Okay, so now coming to the details of the construction. So on the top, we have the high-level schema that we went over. And now we'll try to instantiate that schema. So in our actual construction, the statement will consist of a verification key for a digital signature scheme. And the witness will consist of the following 3 parts. So it will consist of a digest D. Note that at the time of creating the ciphertext, we don't know the digest because we are encrypting, but we don't know what will be the subset of the ciphertext that will be selected. So the digest itself is part of the witness. Another witness is the signature. And the third witness is the opening proof for some ID in this digest. And the relation that we want to check is the following. Again, recall that we had 2 conditions. The first condition is that there should be a valid signature on the digest D. The second condition is that there should be a valid opening proof attesting that the ID is in fact part of the digest. Okay, so now if we use the BLS signature scheme, then your verification constraint looks like the following. You pair the signature with the generator, check whether it is equal to the verification key paired with hash of the digest D. And if you use the KGG commitment scheme, then the verification looks like the following. You pair the digest with the generator and check whether the opening proof paired with some tau minus ID in the exponent is equal to the left-hand side. And this tau is part of the setup of the KGG scheme, G to the tau. So these are the 2 verification constraints. The issue is that there is a nonlinear operation that you're performing on the digest here. And if you have this nonlinear operation, it's not clear how to efficiently convert it into an encryption scheme. So we want to somehow remove this nonlinearity. So how do we do that? So as a warm-up, we can just not hash, right? We can just remove the hash completely and just pair the digest with the verification key. But this is not secure because you can forge signatures if you just remove the random oracle out of the BLS signature scheme. So the tweak is that if you just add a random group element whose discrete log is unknown, then this will give you a one-time secure signature scheme, which means that as long as you don't sign twice using the same alpha, then this is fine. So now you can see that we are no longer performing any nonlinear operation on the digest T. And in practice, you can generate this alpha by hashing some public value, which is, let's say in the blockchain context, you can hash a block number. Okay, so now coming back to like the details, we remove this BLS signature scheme with this modified BLS scheme where instead of hashing the digest, you just append a random group element, add a random group element to the digest. Okay, so now you have these two constraints for BLS checking, BLS signature checking and KGG proof checking. And you can arrange them and rearrange the constraints and put this into a matrix form like this. And so think of this matrix as some public matrix A paired with some witness W equal to some public vector B. So people call this pairing product equations in the literature. So once you have this form, creating a witness encryption scheme out of it is very easy. You just to encrypt some message M, you sample a random vector R, and the ciphertext contains of two components similar to Algamal. So you have R times A, and then R times B plus the message M. So this will this R times B basically acts like a one-time pad if your witness W is not known. And to decrypt, given the ciphertext, you just pair the first half of the ciphertext with the witness W. And if the witness is correct, the R times B term will cancel out with R times A paired with the witness W, and you will get the message. So we show that this leads to a secure scheme, secure batched identity-based encryption scheme in the generic group model. It's an open problem whether we can prove security in non-idealized models. We also point out a bunch of interesting applications in the paper for this primitive, including, so mempool privacy is something we went over, but there are other applications like sealed bit Dutch style auctions, adding fairness to unfair dishonest majority MPC, and privacy preserving options trading. We also showed that we can add CCA security by like in a generic way using this existing technique of appending a signature scheme alongside an IBE scheme. And in terms of efficiency, we also implement this and tabulate the cost of different procedures. So as you can see, the key computation and the encryption runtimes are just do not scale with the batch size. For digest computation, it's same as KGG digest computation, which scales quasi-linearly in the batch size. And decryption per ciphertext is like computing opening proof for KGG openings, which also scales quasi-linearly with the linearly with the batch size. We also compare. So I pointed out during the start of the talk that there's this prior work where there's this expensive per batch setup phase. So we compare with this work. And we tabulate the end-to-end runtime for decrypting an entire batch of ciphertext. And as you can see, our scheme is much more efficient than this previous work, even without accounting for their expensive setup phase. With their expensive setup phase, it's orders of magnitude better. Thanks.
We have time for one quick question. Maybe we can take questions offline. Thank you very much, Amit.